Okay, so let's use some examples, which should be quite interesting. This is an example of a current transformer. Its accuracy is guaranteed for 50 and 60 hertz, but it can measure from 30 hertz to about 5 kilohertz. The measurement ranges from 1 milliamp to 1,000 amps. This can be clamped around 1,000 amp 50 hertz conductor, and it will allow us to measure that current quite correctly. The ratio is 1,000 or 1 to 1,000, so it steps it down 1,000 times. Hence, the current at the secondary will be 1 amp for 1,000 amps. The errors for the full range are 0.3% of the current value and 0.7 degree of the phase shift, and these are used for power quality and energy metering as well in some cases. In order to achieve that proportionality, the burden has to be 1 ohm. It cannot be more than 1 ohm, and this is because, as I said before, the impedance of the secondary winding has to be much greater than the impedance of the load. And in this case, it's at least 180 ohms. It can be more, depending on frequency, of course. And that's why it limits it at the 30 hertz, because if we go lower, then the impedance drops, and that condition is no longer met. But there are other requirements here, because obviously this is just a measurement. What else is required? A mechanical performance is required. If we want to clamp this around a conductor, the jaws have to open enough to be able to clamp around that conductor. If you open too little, we wouldn't be able to clamp around something which carries 1,000 amp, which we can see is not going to be a small wire. There's a magnetic core which is split, so as it closes, the mechanics of that clamp, it has to align that core such that it perfectly mates. If it was slightly shifted, we would lose some of the cross section, and that would impact especially on the high current range. And of course, the plastic, they have to be strong. They cannot be affected by temperature to whatever limit is defined. The safety standards, for example, state that devices like this, they have to survive a drop onto a concrete from 1 meter. And the device can be affected by this on any level, but not safety. It still has to be safe to clamp around something. It doesn't have to work, it doesn't have to be accurate, but it mustn't be unsafe, which obviously puts quite a strong requirement on the plastics. And this is exactly what I said related to safety. But there are other things. Over voltage protection, because this is a current transformer which is designed to be connected to something. The burden is not inside the clamp. The burden will be in the device which is connected to that clamp, right? So if there's nothing connected to this clamp and we clamp around something, the transformer circuit is not closed, so very high voltages could be induced. User has to be protected against that, and this is done by, there's a bit of circuit inside which will basically clamp that voltage to not more than about 24 volts. So it's perfectly safe for anyone to handle this and clamp around something and not be harmed by the high voltages involved. Obviously, there has to be a label which tells the user what voltages and what currents they can use this part of the device. There has to be a tactile barrier, and the tactile barrier is this bit you can see here. So if I'm handling this device and going into a very tight corner or something, my hand wouldn't slip and go onto the conductor. It has to be very ergonomically designed, so it's easy to open, easy to hold, but also so my hand doesn't slip towards the high voltages possibly. And this device is rated at Cat 3 600 volts, which I will explain in details exactly what that means. Just to show you some errors in practice, if we take this device, and the red line you see there is the specification for it. Obviously, the lower currents it is, the more difficult it is to keep very tight accuracy. But for high currents, we have 0.3%. And the solid blue line we can see that over the full range from 1 milliamp to 1,000 amps, the measured error of this current transformer stays below the red line, which is within specification. However, because there's magnetic core involved, if we clamp this around something and there's a bit of dirt or sand or perhaps a squashed bag at the surface, which will introduce some air gap between the cores, then that will impact on the measurement accuracy. And we can see that it no longer holds on to specification at high currents. And the users, they have to be aware of that. There are ways of overcoming this, and you might see on some other versions, not on this ones, because this is rated for higher voltages, hence no sharp corners can be involved. It has to be flat. But some other versions you might see, they might have a number of teeth which will engage, and that will improve the immunity for any gaps which might be between the cores. And the angle error, I'm not showing it here just for clarity, but it's below half a degree for the full range as measured for this device. I mentioned before CAT 600 volts. What is a CAT? Right? If you ask Google what CAT is, you may, for example, get that. Okay, it is a CAT, but not the one we're interested in. Let's look at an example of power supply to a building. We have our power grid, which goes outside to a transformer, and that cable or overhead wires, they will be connected to the building, which then goes to distribution board. There will be fuses or circuit breakers at the distribution board, which then are distributed to our sockets. And we have a, for example, 12-volt bench power supply connected to a socket, which then drives some small resistor. So using this very simple example, we can say that CAT1 is there. It's anything below that resistor, below that first fuse. And we can immediately see that the division is going to be the amount of energy involved somewhere. With 12-volt power supply bench, there's very little energy involved. There's no practically danger to the user. Hence, CAT1 is not even marked on multimeters. It's just the levels of voltages and currents is stated. There's no need for that. CAT2 is with, let's say it's measurement category 2, is stated for something which can be used at a mains voltage. And obviously, there has to be voltage stated at which voltage we are talking about, because, for example, in the States, they use lower voltages, 110 volts, as opposed to Europe, which is 240 volts. So also that has to be stated. And then if we go higher, there will be measurement category 3. And measurement category 4 is something which is measured above or beyond the distribution board and the circuit breaker. So we are potentially exposed to very high energy. Whatever the transformer can give us, it will be there. So if we clamp our current transformers, for example, our current transformer around something in such a way that will short two conductors, they would be exposed to very, very high energy levels. And the device has to be designed to either contain that energy or to make sure we are not short-circuiting the two conductors. So for instance, if we have a device which, like this one, it is rated at CAT4 600 volts, it means that it has to have double insulation everywhere between any parts the user can touch, which means for voltage spikes and other things that the required insulation is 8 kilovolts between the parts user can touch and between the rest of the circuit. And this is defined by international standards, IEC 61010, which is very, very specific definition of how this has to be met. One of the things I can show you also, you can have a look at, is that the double insulation and the 8,000 volts insulation has to be between the outside and the inside, for example, of the core. So any plastic which goes around that, any casing, it is designed in tongue and groove. So there's not just plastic which is buttoned, even if it's glued, there's a possibility of voltage going there. There's always tongue and groove. So there's much longer path between the outside wall and whatever is connected to the system potentially. So this was just a current transformer. Now I will say something about double clamps. What is it, that double clamp earth tester? The earth testers are designed, what the name indicates, to testing the earth connections. So say we have a system. In this case, it's a number of poles carrying some overhead lines, each of which is connected to ground with some grounding electron for safety. So what we can see that we have those number of electrodes, and if we look at the electrical diagram, we can say it looks more or less like this, right? We have our main electrode, which is then shorted with all the others at the top, and there is some ground resistance, and all of them are then shorted by the ground. So equivalent circuit will be something like that. And if we then look at it and say that there's a number of these, I mean, many of these electrodes, more than 10, say. The combined resistance of the many electrodes compared to the electrode under test is going to be much, much lower. Effectively, we'll be tending something like that, where we have a short circuit anywhere else, but at the electrode we try to measure. So what we can do then is we can clamp our two devices around that electrode. One transformer will be inducing voltage in it. Because we have resistance, we have a loop, a current will flow. We can then clamp another transformer, measure that current. Knowing voltage, knowing current, knowing Ohm's law, we can calculate what is the combined resistance of that loop, which will allow us to very quickly assess each of the electrodes. Obviously, there's error involved because we are assuming that all the others are much lower than our primary electrode, but it can be shown that in real life it saves a lot of time. The other alternative is we would have to break that connection here, install an ohm meter and measure that value, which then becomes very time consuming. Whether with a device like this, we can just go there, clamp around something, if we know that the rest of the system will conform to our assumption, and we will get very quick answer. So this is how it was done. There was a bit of device with the two transformers connected to it. And you can't see in this picture, but that switch is positioned at double clamp method. And you can clearly see the two red clamps. And basically, the same clamp is used as a voltage transformer and as a current transformer. Because it's just a transformer, as I said at the beginning. It's just a number of turns. So one clamp is driven to generate some voltage in the loop. The other clamp works as any current transformer and measures that voltage. Sorry, measures that current. And then the resistance is calculated. This particular tester is a multifunction tester. I mean, it can perform any other measurement in terms of measuring earth resistance. It can measure 2-wire, 3-wire, 4-wire, all the regular ways of measuring resistance of the earth. It can measure current. So if there's any current flowing in that electrode, because we have a current transformer, just clamp around it and see what that current is. And this value is only 20 amps because there's no need for more. I mean, the leakage you wouldn't expect to be very, very high leakage current in that electrode. It can measure just voltage. It's a voltmeter as well. It can measure resistance up to 200 kilo ohms. It weighs about 1 kilo, just a device without the clamps. Clamps are a bit heavy as well. And this one is category for 100 volts. So we can see that we cannot connect this instrument straight to our power socket because it is not designed to work with this sort of voltages. In double clamp mode, we use two transformers, which basically are exactly the same transformer. It can measure up to 200 ohms because then that method is only sort of approximation of something. You cannot achieve as good accuracy as with the other methods. However, the clamps, as you can see even on this image, they have to be separated by a certain distance. This is because our voltage transformer is excited and it generates magnetic field around it. Because the currents induced are so small, then that electromagnetic field around the voltage transformer can affect the current transformer. So you have to keep it in physical separation. If you would want to bring them closer, there's really only one thing to do, is to introduce shielding. And this was part of the project we did with Wolfson Center, which we look at how close we can bring those two, and can we make sure the shielding will stop that harmful effect of voltage transformer and the current transformer, not related to the loop, what we want to measure, but the direct interaction between the two.